Yes, sir. Good morning to all the distinguished guests who have joined us for this on the second day of International Conference, TechCube third sponsored International Conference on Recent Advances in Renewable Energy Sources 2021. I welcome all our dignitaries. Without further ado, let me start with the technical sessions of today. The first technical session of today will be chaired by Dr. S.A. Sharif sir and Dr. Kishore Kumar Sada Sivoni sir. Sorry for the mispronunciation. Before that, let me give a brief introduction about Dr. S.A. Sharif sir. Sir is a tenured professor of mechanical and aerospace engineering and is the founding director of Wayne K. and Laila L. Masood HVAC Laboratory, the director of the Industrial Assessment Center, and the director of the Mobile Engineering Laboratory at the University of Florida. Sir has also served as the co-director of the Southern Eastern Center for Industrial Energy Intensity Reduction at the University of Florida. Sir is a Life Fellow of ASME, a Life Fellow of ASHRAE, a Fellow of the Royal Aeronautical Society, Associate Fellow of AIAA, a Vice President of Commission B2 of the International Institute of Refrigeration. He is also member of the Advisory Board of Directors of the International Association for Hydrogen Energy and a founding member of the Board of the Directors of the American Society of Thermal and Fluid Engineers. He currently serves as an ABET program curator in mechanical engineering and as a technical editor of the ASME Journal of Solar Energy Engineering. He has also served as the technical editor of the ASME Journal of Thermal Science and Engineering Applications. Dr. Sharif sir has given over 150 invited lectures worldwide and has received many numerous awards, some of which includes Japan Society of Mechanical Engineers and NASA. Dr. Sharif sir has over 400 publications, 22 book chapters, 1 book and 2 US patents. We are honored to have you, sir, with us. I request sir to start with the technical session with his presentation.
Thank you very much. I appreciate the very kind words that you have.
Thank you so much, sir.
And it's my pleasure to be with all of you today. And if I may, I would like to share my screen. So if you allow me.
Please share your screen, sir.
Yes. Let me try one more time. Okay, I'm having some difficulty here. It says I must grant permission.
Sir, the permission doesn't need to be granted in Google Meet. You just have to go and present now. Then you click on either the window or entire screen.
Oh, okay. If I click either one of them, I get this.
You get that some icons are there, so you have to click on the icon that you want to share, the file that you want to share.
Okay, let me try.
Then you have to click on share button.
I think I'm having difficulty sharing the screen. May I get out and see if I can come back in?
Okay, sure. Or you can share your presentation with me. I'll share it from here.
Okay, let me email it to you. Okay.
Sure, sir.
Can you give me your email address real quick?
Sure.
One second.
I'll write it in the chat box.
Yeah. What is the first letter?
vfuskele, so VFUSKELE at yahoo.com.
V E
S V
R
S.
K. Yeah, I got it. Okay.
Yeah.
At
Okay.
yahoo.com. Okay. All right. Let's see if I can share the screen. Okay, I've sent it to you. Okay.
Okay. मेल क्यों नहीं आ रहा है?
You got the email, correct?
Not yet, sir. I'm just trying to do it. इसे शेयर करूँ? मेल ही नहीं आ रहा है. So I haven't received the mail yet, sir.
I beg your pardon?
I haven't received the mail yet, sir.
You have not received it.
No, sir.
I could send it. I know it went through. Let me.
If you could WhatsApp me, sir.
I sent it to VFUSKELE at yahoo.com.
Yes, sir. That's correct.
It has not arrived yet.
Yeah, you do one thing. You send it to gmail.com. vfuskele at your same ID with gmail.com.
You have another email address?
Yes, sir. It's vfuskele at gmail.com. Same email ID with Gmail on Gmail, sir.
Okay, enough. The same email but at gmail.com?
Yes, sir.
Okay, thank you. Let me try that. Okay, I sent that to the Gmail.
Sure, sure. I'll just see.
Did you get it?
Not yet, sir.
Okay.
Sir, I got it.
Okay, good.
So I'm sharing.
Okay.
Is it visible?
Yes, sir.
That's
Okay.
good. All right, so
You can start.
let's start, and then you're gonna move the slides forward, okay?
Sure, sure.
All right, so the title of the presentation is Latest Advances in Achieving Net Zero. Next slide, please. The outline of the presentation is, first I'm going to talk about the difference between energy carriers and energy sources. And then I'll talk about the background of the energy use in the United States and the goals established by the Department of Energy and the strategy employed, both in terms of energy efficiency as well as renewable energy. And then I'll talk to you about getting to zero. I'll give you a status report from the New Buildings Institute. I'll give you some statistics of the first 10 zero energy buildings in the United States and give you examples in one of those zero energy buildings in Kapuni Village in Hawaii. I'll talk about the California experience, and then I'll give you examples of some recent energy efficiency projects and then some conclusions. Next slide, please. The difference between energy carriers and energy sources. Energy carriers are not simply carrying energy like gasoline, hydrogen, and electricity. Energy sources are primary energy sources such as solar, nuclear, and coal and oil. Next slide, please. This is a slide showing the projected energy consumption in the United States, and you can see that from the 1980 all the way to 1235, you can see the projections in each and every category of energy sources, oil and coal and natural gas, liquid biofuels and renewables. And you can see that in all cases, there is an increasing trend. But in the case of oil and coal, there is a stabilizing trend that will probably continue to be about the same level as it was in 2010. Next slide, please. Historically speaking, you can see what the brown line is and the blue line. You can see how the brown line, which represents per capita energy consumption, has been going down because of the efficiency that we have been able to achieve the energy efficiency that we have been able to achieve, but the overall total energy consumption continues to go up, and that's the blue line. And then you can see at the very bottom, very faint light blue, and that represents the renewable energy consumption, and that is going down, but you can see that the huge difference between the renewable and the total. So it's still a very small percentage of the total. Next one. This is showing the primary energy consumption by the major source in the United States. The numbers are as of 2017, and you can see the different colors in the pie chart. Petroleum is still 37%, natural gas 29%, coal 14%, nuclear is 9%, and then renewable is only 11%. And then within renewables, you're looking at geothermal, 2%, solar 6%, wind 21%, biomass, biofuels, and so forth. Next slide, please. This is showing the relationship between the primary energy consumption by source and where the energy is being used and the sector that it's being used. The transportation sector, industrial sector, you can see the electric power sector, the residential sector. You can see that there is a lot of lines interacting from different energy sources to the different sectors. Next slide, please. This is the U.S. primary energy consumption by major sources, and you can see that the natural gas is the largest, followed by crude oil. This is production, not consumption. So this is the difference between that slide and the previous ones. Next slide, please. Currently, the building consumption constitutes about 40% of the primary energy, and out of that, approximately 70% of the electricity in the United States. The commercial buildings and the primary energy consumption grew by 70% between 1980 and 2010. And the energy consumption is projected by the Energy Information Administration to be about 22% growth between 2010 and 2035. The residential building homes built between 2000 and 2005 use less energy, about 14%, less than the homes that were built in the 1980s, and about 40% less than the homes that were built in the 1950s. Next slide, please. This is the areas of building energy use for the commercial side. And you can see here that there is so-called regulated versus unregulated. And in the unregulated, there is something called the SEDS. That is essentially the State Energy Data System. And that is an adjustment to try to reconcile the supply side and end user side. You can see that the space heating is still very large. The water heating is very large, and then everything else is a smaller part of the pie chart. Of course, the third one is going to be the space cooling. Next slide, please. The same thing, but for the residential sector, you can see that space heating and, of course, lighting is a big player. And space heating and space cooling and lighting are almost 50% of the total energy use. Next one. There are several non-governmental organizations that have played a significant role over the years in improving the energy efficiency, and those organizations are many. They include ASHRAE, the American Society of Heating, Refrigerating, and Air Conditioning Engineers. They have building codes that have actually changed over time due to the different standards of ASHRAE. Standard 90.1 is a good example. It just got published in 2019. There's also the International Green Construction Code that played a significant role. International Energy Conservation Code that was introduced in 1998. And there is something called the International Energy Conservation Code that was a latest release was in December 2019. And they call it the 2021 International Energy Conservation Code. There's also the Energy Star program, which is part of the Environmental Protection Agency, and that was significant. Also, the leadership in energy and environmental design, and that we call it that LEED, and that promotes certification systems for identification of high efficient performance buildings. So they give them ratings, gold ratings and silver ratings and so forth. Next one, please. You can see actually how the use of the different tools that were developed by the non-governmental organizations have resulted in a reduction in energy consumption over time. You can see the trend line going down and efficiency is going up. Next slide, please. The goals established by the Department of Energy include by 2025, they want to achieve 75% energy reduction. And by 2025, they want to create the technology and knowledge for cost-effective commercial buildings, so-called ZEBs. Next slide, please. This is the New Building Institute. They published a definition, official guide for the definition of what a zero energy building is. It's a building that produces enough renewable energy to meet its own annual energy consumption requirements and therefore reduce the use of non-renewable energy in the building sector. This definition also applies to campuses, portfolios, and communities. The National Renewable Energy Laboratory published a guide that have recommendations for replicating specific successes of early adopters who have met their energy goals while controlling the costs. This guide provides what they call user-friendly guidance for achieving a zero energy K-12 school building. It includes a set of energy performance targets for all climate zones, and there are strategies on how to achieve these energy targets throughout the guide that are provided throughout the guide. Next slide, please. Then the New Building Institute, they published a report every 2 years. This is the 2018 report that was published. It summarizes the growth and trends from nearly 500 certified and verified emerging zero energy projects across the United States and Canada. In the first report that was published in 2012, which was entitled Getting to Zero Status Update, the National Buildings Institute reported on 60 commercial and multifamily buildings or projects. The 2018 report lists a steep curve upward, with the National Buildings Institute count increasing over 700% in about 6 years. Next slide, please. And according to the Department of Energy Zero Buildings database, there are, in 2014, as of 2014, there were 126 buildings in the United States that were considered to be net zero. The distribution of these buildings are according to the climatic zone, and there are 8 climatic zones in the United States. You can actually see them. Now there are 7 listed here, but there's actually a small zone that is in the subarctic zone. We call it zone number 8, and only found in Alaska, and it's not shown here because Alaska is it's a bit detached, geographically detached from the continental United States, on the contiguous United States. And you can see that there are 7 climatic zones, including zone 7, which is a very cold, and then the cold zone is zone 5 and 6, mixed humid, 4A and 3A, mixed dry, hot and humid, hot and dry, and then the marine. These are all counties with a sea moisture regime. Next slide, please. And according to the New Buildings Institute status report of 2018, you can see the number of buildings have gone up almost exponentially. If you go back to 2000, there was hardly any net zero building, and then by 2018, there's almost 500 buildings now that are categorized as net zero. Next slide, please. And this is the distribution of the number of zero energy buildings. You can see how from 2012 to 2014 to 2016 to 2018, the numbers have gone up pretty significantly. Now there are 67 zero energy verified buildings, and then there is 415 what we call emerging projects that have not been verified yet. Next slide, please. And this is a distribution according to the map in the United States. You can see that the blue lines, the blue color, is the darker the color, the better. So you can see that in California they have about 214 count buildings. The next region is in the northeast. They have 73, and then the southeast they have about 50. And you can see that the distribution is the number inside each state gives you how many net zero energy buildings there are. Next slide, please. This is the same thing, but the 2014. You can compare the 2014 to the 2016. It's a huge difference. In California, there's 10. There was 10 in 2014. Now there are over 214 as of 2018. So next slide, please. Also from the New Building Institute, the status report, this is the climate zone distribution of net zero energy projects. And you can see that zone 3B and 3C in the middle have the largest net zero buildings. And if you can follow the color, the orange color, you can see where they are on the map, primarily in the southeast and in the southwest. Next slide, please. And also, they have the zero energy buildings that's categorized according to size. You can see, depending on the size, the building. Let's go back to the previous slide. The building count within the size group, and you can see if you have the square footage between 0 and 5,000. You have that's the dark red, and then from 5,000 to 10,000, that's the orange, and then from 10,000 to 25,000, that's the yellow, and so forth. So you can see the distribution based on the size for both the so-called verified buildings and then the so-called emerging buildings. They don't want to call them the non-verified; they call them emerging. It's a nicer name for that. Next one, please. And this is the type breakdown, the building type breakdown, whether it's for education, or office buildings, or multifamily, or public assembly, or mercantile, public order and safety, warehouse and storage. And then also in the education category, you can see they broke it down into K-12 and higher education and general education. Next slide, please. And this is the breakdown according to the building ownership, whether it's private for-profit or private multifamily or private not-for-profit or public county or public city or public state or public federal. Next slide, please. And this is also the building count distribution based on the year of completion. You can see that there has been a huge increase. The dark purple color is private buildings, and then the lighter color is public building. Next slide, please. This is the building count again as a function of the building type or the building ownership. Again, listed, just drawn in a different way. Instead of the bar chart, they have it in graph line. Next slide, please. And this is a zero energy building based on what they call the jurisdictional scores, and they have given a score. This is basically a way to rank these states based on their adopted energy policy. So there is a category or an index that they develop to categorize the states on the basis of how aggressive they are towards implementing net zero. Next slide, please. There's actually a database that you can go online and you can download it. It's so-called Getting to Zero Building Database. and it's an interactive database that you can work with. It's a very nice database if you try it. Next slide, please. And this is showing a part of what the database does. You can actually select what you want, and it will interact with you, and it will give you where the buildings are and what their type is and all that. Next slide, please. Now there is the so-called Florida Solar Energy Center, and that's located in Cocoa Beach, Florida. In Cocoa Beach, Florida, which is a small coastal eastern coast of Florida city that is about 55 or 60 miles east of Orlando. And in the Florida Solar Energy Center, and that's a state-owned research institution that's part of the University of Central Florida, which is located in Orlando. And the Florida Solar Energy Center, they have an energy research center, and they have what they call the Home Energy Rating System, or HERS. That index determines the likelihood of a home performing at zero energy for a typical occupant. So they are working with residential section, and they were able to develop this nice tool that can be used to encourage net zero. They give a score. If you have a score of 70, a score of 70 is projected to use 30% less energy. So you can see that what 70 actually means. 70 means that you are using 30% less energy. All right, next slide, please. And they published a report on the comprehensive modeling of optimal paths to reach nearly zero energy buildings for new constructions in Europe. They investigated that particular market, and it described results obtained from the modeling of the net zero energy buildings for new construction in Europe. They use energy performance software called Energy Plus, and the model performs hourly sequential simulations that shows how to best achieve net zero in home design at the lowest possible cost. And they used 36 different representative locations across Europe. And they found that the energy reductions of about 80% and beyond are economically feasible for new construction, although a mix of selected measures vary strongly with the climate. And of course, Europe has a vastly different climate depending on where you are. So they showed a broad approach to efficiency mixed with renewables, and that was achievable and feasible for several locations in Europe. Next slide, please. Let's talk about the California experience, because California has always been very aggressive in leading the country. So this new lab report outlines is what they call getting to neutral. And that was published in January of 2020. They outline ways California could reach the goal of becoming carbon neutral by 2045. Next slide, please. In the picture here, you see the person. There are two people cutting a ribbon. The person that's on the right side of the one holding the scissors is Governor Jerry Brown, or shall I say former Governor Jerry Brown. He was a two-term governor of California. In fact, he was a two-term governor of California on two separate occasions. Very popular guy, very liberal and aggressive, and in favor of climate change and all that. So California has done a lot. If you can go to the next slide. They have set a bold course to achieve statewide zero net energy in the next 2 decades. All new residential construction will be zero net energy by 2020 in California, and that is actually happening as we speak. And all new commercial construction will be zero net energy by 2030. And 50% of the existing commercial buildings in California will be retrofitted to net zero by 2030. Next slide, please. Now, I'm going to talk to you about some of the buildings that have historically been, or the leading energy, net zero energy buildings that the original ones, the 126 buildings. According to the climatic zone, and I told you that there are 8 of them, you can see the distribution of the different climate zones. Next slide, please. So those, I'm going to select 10 of those buildings. I call these pioneering ZEB buildings, or net zero energy buildings. And I'm going to show you some of the pictures in the different climatic zones, and then I'll focus on the one in Kapuni Village, Hawaii. Next slide, please. This is the one in Kapuni Village in Hawaii, zone number 1. And you can see the building. I'm gonna zero in on it in a little bit in the next slide. But I just want you to take a broader picture of where the building is. Next slide, please. It's a single-family residential home. And I must have eliminated the slide that shows, go back to the previous slide for just a second. In that particular building, they have, of course, you can see the photovoltaic panels on the very top. And also they have different insulations that they put in at different locations. And the types of windows that are there are airtight and all that. So there's quite a bit that I could talk to you about that particular building. But unfortunately, I don't think I have the slide. I have the slide to show the details of the different construction details. Next slide, please. And this is the student-built houses powered exclusively by the sun. They have every year they have what they call the solar decathlon, and the students compete and they actually build zero energy buildings every year, model buildings that they can compete and win awards for. Next slide, please. Now I'm going to switch the topic, and I'm going to talk to you about examples of recent energy efficiency project real quick. I know we're over time, so I'm going to go very quickly on that. There are several projects that are funded by the Department of Energy, including the air source integrated heat pump and cold climate heat pump, next generation rooftop unit, residential absorption heat pump, commercial integrated heat pump with thermal storage, and a separate sensible and latent cooling, membrane-based air conditioning system, and solar absorption cooling system to reduce peak loads. Next one. There are more examples for what they call water heating. They have an absorption heat pump water heater, and a commercial absorption heat pump water heater, and a carbon dioxide heat pump water heater, and a residential absorption heat pump water heater, and a combined water heater and dehumidifier and evaporative cooler, and a commercial CO2 heat pump water heater and maximum technical efficiency electric heat pump water heater with low global warming potential halogenated refrigerants. All those are different projects that are being funded by the Department of Energy. Next slide, please. There are many other examples of energy efficiency projects, including what they call the miniaturized air-to-refrigerant heat exchangers that's done by the University of Maryland. There's a gas heat pump for building space heating. There's a company called Stone Mountain Technology that are working on it. Lawrence Berkeley National Lab is working on highly insulating windows using smart automated shadings. It's computer-based, and they can actually, the shades can make decisions on their own based on the time of the day of the year, and the orientation of the buildings, and the sun, and the wind, and all that. There are dynamic windows program at National Renewable Energy Laboratory that has been developed. There's also dynamically responsive infrared windows coatings at the Pacific Northwest National Lab, and the next generation building envelope materials at Oak Ridge National Lab. Next one, please. This is an example of the miniaturized air-to-refrigerant heat exchanger at the University of Maryland. And if you go to the next slide, I'll show you the chart that shows, well, let me first tell you what the purpose is. The purpose is to basically build smaller heat exchangers that have very small size. So they would be miniaturized. You can sort of put them in your pocket. Next slide, please. And they have a performance target with at least 20% less volume and 20% less material and 20% performance, more performance than the current designs. There's several organizations that are teaming up: Oak Ridge, Luvata, a private company, International Copper Association, Wieland, and Heat Transfer Technologies, among others. Next one, please. And if you look at this chart, you see actually, the port hydraulic diameter is a number on the horizontal axis that indicate how small the heat exchanger is. The smaller the number, the smaller the heat exchanger. And then on the vertical axis, you have what they call the compactness, which is the ratio between the volume and the surface area. And you can see that actually, you can see a lot of data points on the left side of the chart and on the bottom side of the chart. So what we want is we want the small hydraulic diameter with a large compactness. So you want to be on the top left corner of the chart. That's where you want to be, so that it will be a small size with high compactness, and that way you will have a more efficient heat exchanger. Next one. And this is showing the pressure drop as a function of the heat exchanger volume. And of course, many of you who know heat transfer know that when you want to increase the heat transfer, you have to also keep an eye on the pressure drop. So the heat transfer and the pressure drop is really a one problem project that you have to work on. You cannot just increase heat transfer without regard to the pressure drop. So the pressure drop here is very important, because as you increase heat transfer, you will necessarily increase the pressure drop because of different things. When you have more fins or more blockage or this or that to try to make the fluid shake hands more, that will become more of a blockage towards the movement of the fluid, and therefore increase the pressure drop. Next slide, please. This is an example of the project that I told you about, the Lawrence Berkeley National Lab. And these are the so-called smart automated shading. And I will show you how it works. Go to the next slide. The project goal is to create highly insulating windows with integrated sensors and control logic and motorized shades. The default control algorithm in these windows will minimize heating and cooling. So if you are in the summer, it will minimize cooling, and if you are in the winter, it will minimize heating. And it optimizes the performance from links to the utility meter, the home automation, the thermostat, internet data, etc., etc. Next slide, please. This is how the flow chart kind of works. You measure the indoor temperature, you measure the outdoor temperature, you make a decision. Of course, all of that is done by the computer program as to whether the shade will close or open or partially close or partially open. So all of these decisions, it's a what if type of a loop. And if you are between this and this, you go to that path. If you are greater than this, you go to the other path, and so forth. Next slide, please. And in this project, the smart window has a number of integrated sensors, and the control algorithm basically evaluates if the homes should be in the heating mode or the cooling mode or the neutral mode. Of course, you have an override option that you could also, where the occupancy can actually make the decision over and above what the control algorithm would do. Next slide, please. In conclusions, there is an effort going underway at finding a solution to the world energy problems. Part of the effort is directed to establishing a permanent energy system by investigating renewables, such as hydrogen energy, for example, which is being revisited by the Department of Energy these days, after an early start back in the 1980s, and then a hiatus 15, 20 years later. And then there is a resurging interest in hydrogen energy, what they call the hydrogen economy now. Another part of the effort has been directed at finding better and more efficient ways of conserving the available energy sources. And I showed you examples of the current efforts in both areas of those technologies. So that concludes my presentation. I apologize for being over time, and I am happy to answer any questions that you have.
Thank you so much, sir. The session is open for any questions.
Anybody would like to ask any questions? So I have one question. Can you throw some light on the type of heat exchangers that these efficient energy buildings are using, which is taking care of the compactness as well as the increased heat transfer?
Right, exactly. That is a project, that's an ongoing project for a long time now, has been funded by the Department of Energy and the University of Maryland, the Center for Environmental Energy Engineering. It's led by Professor Radermacher, who is a very well-known researcher in the University of Maryland. Radermacher and his group have been working very, very hard on developing these new heat exchangers that are very compact, with very high compactness and very small port hydraulic diameters. So it's actually a multi-year project. Has been going on for I'm guessing about 50 years now, and at least. And they have made some really good advances. You could search in scholar.google.com. You can search for a compact heat exchangers under Professor Radermacher, Radermacher, and you will find a lot of good papers to read. Yeah.
Okay, sure, sir. Thank you.
Welcome.
Anybody else would like to ask any questions?
Nice presentation, sir. It's really good, really useful information. Thank you.
Thank you.
Thank you, Reddy, sir. Thank you, Sarif, sir, for your wonderful presentation on energy efficient buildings, which is the need of an hour. Thank you very much once again. So without any delay, I'll switch over to Rajni. You can please introduce the second speaker. Thank you, Sarif, sir.
Yes, sir. Thank you so much, sir. Next in the technical session, we have the talk of Dr. Kishore Kumar, sir. But before that, let me introduce sir. Dr. Kishore Kumar, sir, is currently working in Center for Advanced Materials, Qatar University. He has published 82 journal papers, 12 book chapters, 7 books edited, and 3 patents filed. He has about 10 years of experience in synthesis and characterization of nanoparticles, and also in manufacturing nanocomposites for industrial applications. His area of interest include different types of nanocomposite fabrication, modifications, design and their application, especially sensor, piezoelectrics, actuators, energy storage, dielectrics, 3D printing, and flexible electronics. He is also serving as a managing director for the Emergent Materials General Springem, led by the Qatar University and Qatar Petroleum Company, and editorial board member for the Bulletin of Chemical and Pharma Research. He serves as a guest editor in the Sensor and Transducer Journal and a lead guest editor in International Journal of Materials, Science and Applications. Dr. Kishore sir achievements have been recognized by awards such as Tire and Rubber Industry Leadership Acknowledgement Award, Young Research Scholar of the Year 2017. Engineering College Banswara is highly honored to have you, sir. It's my request that sir should start his presentation on magazine-based nanomaterials for energy storage and other electronic applications. Sir, you can start with your presentation.
Yeah, thank you very much, Ms. Rajni, for your kind introduction. Let me just share my screen. I believe I won't get any problem sharing. Let me just check it. Sharing the window. Let me see that. Yes. Are you able to see that?
Yes, coming.
Yes.
Yes, sir. It's fine.
Yeah. Yeah. So, am I audible perfectly?
Yeah,
Yes,
sure.
sir.
Perfectly, sir.
Yes. Thank you very much. Firstly, let me give my honor to say thanks to Dr. Viresh for giving the opportunity to share my ideas and views, my research, and the team international conference on recent advances in renewable energy sources. So congratulations, you are doing really good job. Keep on doing. So today I would like to discuss about one of the grant which we have been awarded based on the CO2 reduction. And also I will discuss about amexines, what is the amexines of the materials, and how we have been used this material for energy storage purpose and other electronics. So before going, let me just give some brief introduction. I know that we are running late, but just give me some time to introduce myself. So I'm basically working in Qatar University, and you can see that this is the picture of Qatar. It's a very small country, and it's around 25 lakhs people are living. In that 50 lakhs people are Indians. So it's just like everywhere, wherever you go in market, you can just speak, Hindi. That's fine. So we are occupying that one, and also the main source of income for this Qatar is oil and gas. This is the Qatar University building. You can see that it was nicely architected, and there is some importance of this building. Most of the time, we never use any air condition for getting the temperature down, because the head of the buildings, you can see that it's like a cube, and it easily absorbs the air and makes cool the rooms easily without using the electricity. So this is a good thing that we are using, and this is the building where you can see in the down right corner, this building H10, this newly constructed building. In that buildings, we have 7 zones. In that one zone is Center for Advanced Materials, where we are working. Yeah, so basically, Qatar University is focusing on 4 different pillars. One is energy, environmental, and information technology, and health and wellness also, and finally the social change and identity. So I believe this first pillar is the main part of the conference also. So the funding sources, what we have is QU internal grants. I mean, Qatar University also giving the internal funding for all the researchers who are working. And we also have funding resources from the QNRF, that is from government. And also we have funding from the industrial, like for example, Qatar Petroleum, ExxonMobil, or Qatar Aluminium Company. And there are many different industries are existing here. And also the researchers who are working here also applying for other international fundings like the European Unions and the NIH, something like that. So what I basically want to give a hint, like if anyone interested to make a collaboration and apply the grants, we always welcome. You can contact me at any time. So let me just give an outline of my presentation. This is, I will give some little introduction about amexines and how we have been used at amexines for the CO2 reduction, piezoelectric sensors, and biosensors, and future potential application and conclusion. So here is a little introduction about amexine. So most of the people know about graphene because it got Nobel Prize in 2009. I believe, yes, 2008 or 9, I think, yeah. Because I started the work at the same time on graphene, and we have been using the improved graphene oxide method to fabricate this graphene. And later in 2011, Professor Yuri and Professor Mikkel from the University, they have been invented this new material called amexine. This is quite similar to the graphene, but it contains a metal trapped inside. So it is a metal carbide containing different metal like aluminum in between. So what is the parental metal? For example, in the case of graphene, the parental material is graphite. But in this case, for MXene, it's a max phase. So people are using the max phase to make it a single layer using hydrogen fluoride as a chemical material to degrade that into the single sheets. You can see that how it will be delaminated after the etching process. So why we have to focus? Because there is materials such as graphene is the strongest material, but why should also we have to think about these MXenes? If you see about literature in the graphene, maybe 10,000 patents, maybe I believe this is more than that. So why we need a new material? The fabrication process of graphene not really easy to make a single layer thickness. So we need something like an alternative material such as MXene. It has also same strength and then flexible nature also, and high conductivity because of this metallic nature. It's around like 5,000 Siemens per centimeters. And also it is flexible, so you can use it to make the electronics highly flexible and inert to the oxidation. So this is these advantages makes MXene to use more and more in our realistic applications. So here, as I said, so here is the max phase. It contains similar to the graphite, many stacks are there. And then what we use that is aluminum in between that stacks, we will etch with the hydrogen fluoride. Then what will happen, you will get the layers, single layers, like called M4X3, M3X2, and M2X2. Because of this etching process using the fluorides, ions, or oxides, so it's easily dispersed in the water. So this is a very good advantage of the MXene, that you can disperse in water and you can use it. And also, as I said, it is very flexible material also. So because of this nature, you could make a large, wide scale of surface area. For example, you can use casting method to make it large surface areas, and also a rolling method and electrospinning methods. So all these are really feasible for the kind of MXene. But in the case of graphene, we should be very careful that making such a large sheet not really easy way. And the 2011, how they have been reported this MXene is by using some application called EMS shielding. So they got very high EMS shielding, and it is the highest of the man-made. What they have been reported. More than that, they couldn't find. So here you can see that MXene has the highest image shielding. And the reason behind that is the total internal reflection is very high in the case, and also it has high conductivity. So it can stop the electromagnetic radiations. So you can see that how it looks like an hexagonal structure. This is also similar to the graphene, but the metals will be in between that. And you can also see here the picture that how we have been fabricated. People use max phase, and then we etch with the lithium fluoride, or we use the hydrogen fluoride, different fluorides to remove this aluminum. And the fluorine will be replaced. So here is what are the examples you can see is titanium, aluminum carbide, and there are different type of MXenes are existed now. So if you recollect the idea about graphene, in the case of graphene, while you're preparing, so you can prepare single layer, which is nothing but 0.8 nanometers. But it's not really easy case. But in this case, what I said, it is really easy to control the concentration of the hydrogen fluoride. So if you are giving high concentration of hydrogen fluoride or lithium fluoride, so what will happen that it will etch all the layers and you will get a single layer. Or if you want to make a multi-layer, also you can control the concentration of the hydrogen fluoride. So I don't want to discuss much about its fundamentals, but so this is the application of MXene that they are using in a different industrial applications, such as sensors they are using now. They are using in the batteries. They are using the carbon reduction. They are also using in water purification process also. You can see the number of publications are increasing day by day. So let's go to the first part, what we have been done with MXene. So we have used this material to reduce the carbon dioxide. So before that, I will give some introduction about why we have to reduce the carbon dioxide. Because of this global warming, we should be careful about the concentration of the carbon dioxide in the atmosphere is increasing day by day. For example, in Qatar, what they are producing carbon dioxide is very high, huge, because the industries, for example, Qatar Aluminium Company, so they produce aluminium. For 1 ton of aluminium, they are producing 2 tons of carbon dioxide. So what they should do, that there is excessive carbon dioxide, so they really need help of researchers to convert the carbon dioxide to useful fuels, such as ethanol or methanol or formic acid. So our aim is to convert this carbon dioxide using catalysis. So what generally we'll do that when we do the electrolysis of water, you will get hydrogen and oxygen. But in our case, what we want to try is we pump the carbon dioxide through the water containing some aqueous medium. So what will happen that the carbon dioxide will be trapped inside, and then the catalysis will use to convert this carbon dioxide to the different fuels, such as I mentioned, that methanol or ethanol or formic acid. You can see here in the picture that when we give the electric field, it converts into different fuels. But do we think that it's really easy? But in my point of view, it's easy to convert carbon dioxide into different chemicals, but making the selectivity is very difficult. So we need a catalyst that can be used to make selective fuels, for example, copper. So copper can be used to produce methanol selectively compared to the other compounds. So then only you can sell the fuel when after making that one. So so this is the first challenge, is to find a perfect catalysis to make a selective chemical compound. So here in the picture, what I try to explain is, so while forming carbon dioxide to the products such as fuels, so there is an intermediate called carbon monoxide. If catalyst is not able to convert the carbon monoxide to the fuels, so what will liberate that carbon monoxide will convert in carbon dioxide will convert into carbon monoxide only. So it's very dangerous than useful for us. So selecting a catalyst is very important. So in this work, what we have been used at, we use zinc oxide, iron, and MXene doped material, and we have been checked different catalysis properties of zinc oxide alone and zinc oxide Fe alone, MXene zinc oxide iron. So we found that this material shows very good selective reduction of carbon dioxide. So here is the XRD pattern and FTIR, what we have been used to check that really the zinc oxide Fe is doped inside or not. and as I said that MXene was used to prepared by hydrogen fluoride. You can see that there is no peak in the range of 33 to 43. So it was disappear, this peak was. It means that MX phase is converted into MXene. And also, we have been checked that SEM analysis of the material, and we found that MXene Fe zinc oxide contains some edges. So these grain boundaries is very important while converting CC bond formations. And we also found that it is around like 100 nanometer grain size of this zinc oxide doped iron. So this is the experimental setup, how we have been made. It is very simple that we use carbon dioxide to flow through that cell. And the cell contains 3 electrodes, working electrode and reference electrode and counter electrode. We have been coated the material on the working electrode and after passing through the carbon dioxide, so we the products has been detected using the gas chromatography and HPLC. So here you can see that very clear identification of the material is carbon dioxide reduced by using the zinc oxide, and we have been identified very high reduction current here at -1 voltage, because the ore potential is very important in our case because we need to reduce it as much as low. So the catalytic property mainly to reduce the ore potential and make it selective reduction. And also we have been performed some electrochemical impedance analysis to check that whether the catalyst can be reusable, and also it can be the charge transfer is going easily or not. So we have been performed at lower and higher frequency also, and we found that zinc oxide FeMXene has very good reproducibility, and not only it is reducing the carbon dioxide, but also it is stopping it departing during the structural recognition. So what happened that is, so it is also absorbing the carbon monoxide feebly. If we strongly absorb the carbon monoxide, what will happen that we cannot convert it into different products. So here you can see that we have performed in 1,000 cycles to see that durability of the catalysis, and we found excellent durability and containing 80% of residue. Can you see the screen now? Yes, okay. Yeah. Yes. So after fabricating this material catalysis, I mean, for example, the MXene and zinc oxide iron, so we try to utilize in making the robot. So what we have been prepared in our laboratory is, basically I'm a mechatronics guy having some knowledge in the chemistry. So we try to use that knowledge to make the robot. So how we fabricate the robot is to absorb the carbon monoxide from the atmosphere, and we use this catalyst to convert by using the renewable energy. Here is a robot, looks similar to this one, and then we use also software to detect the carbon dioxide by using the electronic nose. Here the electronic nose. So this robot will go through around the campus and then find that where the carbon dioxide is very high, and then it start using the motor to clean it, and then it convert automatically. So this was now we are using in the different industries such as Qatar Aluminium and also KEFAC, what they are producing this high amount of carbon dioxide. So moving to the my next work on this MXene-based piezo-resistives, we have been also prepared some sensor that can be identify the force of fingertips or very feeble forces. So we use the electrospinning materials to make the sensors. So here is how we fabricate. We took the max phase and then we use the lithium fluoride and HCl to make MXene. Because why we have been used this mixture instead of hydrogen fluoride? Because you know that hydrogen fluoride is very dangerous acid, so it's very difficult to use in the laboratory. So we use the in situ method to form this hydrogen fluoride and to make the MXene. And then we have been used also the polymer to mix with this MXene polyamide, and then we make very sponge structures. So what will happen when you press that material, and then it change the force based on the amount of filler inside. So here is the structure, how it looks like, the sensor. So we use the composite in between the two conductive electrodes, and then we use the force to find the sensitivity. Sorry, I'm a bit making faster. to catch the time on. Here is the result that you can see that when we increase the force of the material, it is gradually increasing, and we found that around 20 newtons is enough to find the sensitivity of the material. So we use the equation called relative resistance. So resistance changed by the initial and the after applying the force. So what is the principle behind this is the change. So when we apply the force, what will happen? It breaks the network and change the resistance. So here is the experimental verification what we have been made. So see, we are hitting here the mixing phase material inside the composite, and then we found the signal very nicely, and it is around like 20 newtons. So moving to the next part of my research, so we are also working on the biosensors based on the MXene and the copper oxide, nickel oxide. So the main problem here is number of diabetic patients are increasing day by day in Qatar, even the world also. And we are trying to use the sensor to avoid the pinching. For example, if you have diabetes, you go to the doctor and then they will pinch and they'll check the glucose level. But we are trying to use our material to detect the glucose in the sweat. So by just sticking the sensor on the top, and you can tell that, okay, how much is the glucose content. So if glucose content is high, you can take the medicine. If not, you don't need to take a medicine. So this is to control the precise medicine in the body. What will happen if we take more, amount of medicine is higher, so it will damage internal organs. So here how we have been fabricated, and this is quite similar to the material how we fabricated in the CO2 reduction. So the material what we have been fabricated can be patched on the skin. So here is the results what we have been obtained. When we increase the glucose concentration in the sweat, it is really detecting very nice and then showing excellent peaks. And see, you can see that very nice oxidation reduction peaks, and it is increasing by the concentration. Here is the device which we have been made that can be stick on your skin and absorb very nicely, because we have used the cloth as a sticker. So then what will happen when sweat comes, so it absorbs and it takes the glucose level. And also we check that whether this sensor having the high selectivity or not, and it is very good sensitivity and selectivity towards the glucose. So here is the conclusion of my talk. So without making delay, because I am a bit faster, so please accept my apologies. So the conclusion is the MXene really necessary nowadays to make a different kind of electronic applications, such as mentioned in my slides at carbon dioxide conversion, or you can use the sensors, or you can use the biosensors. And we have been also demonstrated it is a very good sensitive material also. And there are some challenges behind to making this MXenes also, because it has functional groups itself. For example, fluoride. If you would like to remove that fluoride, so we need to make more work to remove the functional groups. So finally, what I would like to say that the material which we have been fabricated, if we keep it in a reactor, and it could save the carbon dioxide. I mean, it's like 37,000 trees performance, the cell it will be. So imagine that if we have large quantities of carbon dioxide from the industries that can easily connect to the reactor and can absorb this carbon dioxide and convert into the useful fuels instead of trees. So before leaving, I just want to give some advertisement. Being a managing editor of this journal, so I'd like to request you all to submit your valuable manuscript to the emerging materials. We will be happy to receive, and also please follow us in the Twitter and LinkedIn. So this is my group, and this work was mainly done by the Dr. Karthik, and also I thank Dr. Viresh and their committee members. Also, I thank Qatar Foundation for giving the funding for a whole group, and also Qatar Aluminium. They are the in-kind supporters for the. Thank you very much. So there is a football World Cup is going to be happen in next year. If someone would like to visit, I will be happy to receive them. Thank you very much.
Thank you so much, sir. Thank you so much, sir. If there are any questions, the session is open for questions.
Okay, hello. Hello, Ashok Kumar, hello.
Kishore Kumar.
We are able to hear you.
Yeah. So very nice presentation. In fact, I enjoyed really very useful information. So just I would like to ask you some small. Did you try with instead of lithium fluoride with ammonium fluoride? Because or which one you think that?
Yeah, you could use any strong acid to replace the aluminium.
Okay.
Because what I mentioned is that instead of hydrogen fluoride, I use lithium fluoride and hydrogen fluoride to minimize the risk. If you want to take more risk, you can use it. In fact.
Okay. So and also regarding your glucose sensor, what is the advantage of using that copper oxide and nickel oxide composite? Or is there any special thing, or
yes, it's a good question. Because of time lag, I'm not able to explain that what is the reason behind that using the materials, but it is making a high selective towards the glucose.
So
and what
like
will happen that at a pH 12, these materials are responding and then making the oxides, and then start the reaction with the glucose enzyme. And when the glucose comes to react with that at that condition, and it starts. So what is the use of MX in them? So these are the materials that reacting with the glucose oxide and producing the electrons. But in the case of MXene, it encourages to the flow of electrons.
So it looks like MXene is like a nice mechanical. What they call it? It is like a nice adhesive substrate or something like that.
Exactly. You're right. So this is quite similar to the graphene itself, but a bit more performance in the case of electronics.
Now, in fact, supercapacitor, I don't see much because compared to your profiles, it is not very interesting. Although people claim MXene can use it for all the things.
Exactly. Yes. You're right.
Reality, supercapacitor, it may not be interesting. Maybe regarding that glucose sensor, maybe my suggestion, I don't know, you can try with some 5 to 10% nickel, lithium doped nickel oxide. So because a nice conductor, maybe you can try it. My suggestion, instead of copper oxide, maybe 5 to 10% nickel doped nickel oxide. You can use that one. It should be because it's a nice electronic conductor. I hope that you get more response. Maybe any students are there in future you can try. I think that is
definitely. To make it more selective, we use these two materials. Okay. But we should be very also careful when we are using the amount. If we are keeping more amount, what will happen? It will be purely conductors, no use. So we have done it. So we have to be very careful while making the composite to know the percolation limit also. Yeah.
Okay. Anyway, very nice talk. Maybe future we'll visit your lab. Okay.
Definitely. Always welcome to visit the lab. Yeah.
Okay. Thank you very much.
We can arrange the visa for if you would like.
Yeah. So in fact, yesterday I given the talk. So in fact, I love the visit. It was nice and a nice presentation. Okay. Thank you very much.
Thank you very much.
Thank you very much, our chairman Saab. I think with him, and also with technology, we are able to. Since I'm in Canada, I think I'm able to meet you people. Great, really great, sir. Really great.
Yes.
Okay.
Thank you.
Thank you so much, sir. Any other questions?
I will be very happy if you ask some questions because it will trigger my mind to think about more, to make new projects. To be honestly, that when we present this kind of talks, the main reason to get the question. So when you give a question, though we may not answer it, but it will trigger us to think more and then apply fundings. To be honest, thank you very much.
Okay, thank you so much, sir.
Yes.
Now
Thank you
we'll
very
start
much.
with the oral presentations. Each one of the paper IDs are requested that please limit the presentation within 15 minutes. And I request Dr. S.H. Sharif sir and Dr. Kishore sir to kindly award the marks for the paper presentation in the evaluation sheet provided, sir.
Yes, yes,
You
I
can
have.
take over from here. Should we start, sir, with the paper ID 25?
Yes, please.
Paper ID 25?
Yes, sir. Great.
Yes, sir.
I'm happy to present the first speaker.
Yes, yes, sir. I am present.
Prashant, please share the presentation.
Go ahead, sir.
Sir, is it visible?
Yeah, it's coming.
Okay.
Yeah, it's fine.
Should I start?
Yeah, please start.
Good morning, all of you. I am Prashant Kumar. I am doing my PhD in MANIT Bhopal. I have submitted my paper on the topic Review on Synthesis of Nanocomposite Material and Preparation of Hybrid Nanofluid for Efficient Heat Transfer. The points I will be discussing is introduction, objective of my review paper, hybrid nanoparticles, preparation of hybrid nanoparticles, thermal performance of hybrid nanoparticle, literature review, and after that summary. Introduction, conventionally we use the heat transfer fluid, which is generally water or ethylene glycol or some oil, which have low thermal conductivity. This fact leads to research in the field to enhance the thermal conductivity of the fluid. When we suspend nanometer size particles in a base fluid, then this type of fluid is called nanofluid, and because of the solid particles have higher thermal conductivity, and thus we get the higher thermal conductivity of that fluid and heat transfer, when we can achieve the higher rate of heat transfer.
What happened, Prashant? Any problem?
Sorry, there is system problem. I am coming.
What is exactly the issue?
Sir, is it visible?
Yeah, now it's visible, right?
Okay, I'm connecting one.
Prashant, you have stopped presenting. Please share the slides.
Yes, sir. Yes, sir. I'm coming over.
Yeah, it's
Is it now?
Yeah, it's visible now. Please go ahead.
Sorry for the disturbance. The heat, as I was saying, that when we suspend the solid particles in the base fluid, the solid particles have the higher thermal conductivity, and hence it enhances the thermal conductivity of the base fluid, and we get the higher rate of heat transfer. When we suspend more than one type of material, nanoparticles in base fluid, then this type of called as hybrid nanofluid, and we can achieve the even more thermal conductivity and the higher rate of heat transfer. My prime objective is to review the synthesis and characterization of different hybrid nanoparticles, preparation of hybrid nanoparticles, and the thermal and the and also I studied the thermal performance of different hybrid nanoparticles in different working conditions. The hybrid nanoparticles can be characterized in three basic categories: the metal matrix, in which we can consider the materials like aluminum, tin, gold, iron, copper, nickel, nanodiamond, magnesium, etc., and silver. In ceramics, we can consider the copper oxide, hematite, silicon carbide, magnetite, silicon oxide, and titanium oxide, nickel oxide, and aluminum oxide. These are generally used as a hybrid material. In polymetrics material, the materials like polyvinyl polymer, PVC, polyethylene, and ethylene vinyl alcohol, propylene is used. The preparation of nanoparticles. Generally, if we simply add the nanoparticles in base fluid, then we cannot achieve a good. Then we cannot form a good hybrid nanofluid. The basic property is we should suspend the nanoparticles with higher stability. To enhance the stability, there are some techniques by changing. We can achieve the higher stability by changing the pH value of the suspension, used as some surfactants or surface activators, and by using ultrasonic vibration. Uh, if the if stability is not achieved, then the solid particles will settle down and form a cluster. This reduces the thermal performance of the nanofluid and reduces the thermal conductivity also. So this is the basic criteria why we should achieve the higher stability of nanoparticles in base fluid. There are two methods to prepare the hybrid nanofluid, which is the one single step method. In this, we heat a we in one method generally give a heat to a thin wire, and within a microsecond it evaporates and convert into plasma. When this plasma comes into the contact of inert gas and thereby condensing the plasma into the nano size powder, and when this powder is suspended in the base fluid, then we will got the hybrid nanofluid. Lee reported that when we enhance the degree of superheat, the size of the nanoparticles decreases, and when we increase the pressure of the inert gas, then also we can get the smaller size of nanoparticles. In two-step method, the nanoparticles are made separately by chemical, physical, or mechanical process, and these nanoparticles are suspended with stability in base fluid. Making a hybrid nanofluid with a two-step method can be economically viable on large scale. This is the reason this method is generally used in many research. Agglomeration can also be minimized by using appropriate dispersing devices such as ultrasonic bath, magnetic stirrers, and high pressure homogenizer and ultrasonic jammers. There were some study which I have mentioned here, that how thermal performance affect the hybrid nanofluid. Chopkar synthesizes aluminum, copper, and aluminum silver nanoparticles in water and ethylene glycol base fluid. He found that at 1% of volume fraction of aluminum copper in water, the thermal conductivity enhances by 70% in comparison to base fluid. And when they mixes the aluminum, copper, and ethylene glycol, the thermal conductivity was increased by 50%. And silver aluminum gives the higher rate of heat transfer in comparison to aluminum copper. BB and Sundara uses the silver and graphene nanoparticles in water and ethylene glycol. He observed that when we increases the temperature of the nanofluid or hybrid nanofluid, the thermal conductivity or thermal performance increases, and by increasing the volume fraction, then also the thermal performance increases. On the other hand, ethylene glycol based nanofluid shows an lesser enhancement in comparison to deionized water. Suresh compared the single particle based nanofluid and hybrid nanofluid, and he found he uses the aluminum oxide and copper in water. He found that the hybrid nanofluid performed better in comparison to single particle based nanofluid, and the Nusselt number was increased by 13.56%. Some other studies I have mentioned in tabular form. All of this study shows that when we increase the temperature of nanofluid, the thermal performance also increases, and when we increases the volume fraction of nanoparticles in base fluid, then also the thermal performance increases. But there is a limit of increasing the volume fraction. When we increases the volume fraction more than some values, then losses are more, and the pumping power required will be more. As summary and conclusion, I found in summary conclusion, the process prepared. Factors affecting the performance of hybrid nanofluid have been extensively discussed. Meanwhile, in this review, the thermal characteristics of hybrid nanofluid were found to be the higher in comparison to the base fluid and fluid containing the single nanoparticles respectively. It was observed that the thermal characteristics of hybrid nanofluid increases with increasing temperature and volume fraction, as I have said earlier, where for some hybrid nanofluid, there are an upper limit for the volume fraction, such as the performance deteriorate at high volume concentration. Most of the research work were focused mainly on the water and ethylene glycol based nanofluid, and very few literatures on the synthesis of oil based nanofluid have been found. For preparation, we generally use two-step method instead of one-step method due to their complexity and expensive. To get high stable nanofluid is still a very challenging task. For single particle based nanofluid, stability can be achieved by some established technique, but when we talk about hybrid nanofluid, we suspended the nanoparticles of more than one material, so there is a problem of stability. So more research is to be done in this direction. From present review, it can be understood that the hybrid nanofluid is a promising heat transfer fluid, and extensive and systematic experimental research work have to be carried out to understand the science behind the enhancement in the thermal and rheological properties, and to develop various properties model for a wide range of performance affecting parameters for the variable and sustainable commercialization of hybrid nanofluid in various fields of engineering research. Thank you, all of you.
Thank you, Prashant. And if anybody having any questions, please may ask.
Yeah, Mr. Prashant.
Yes, sir.
Yeah, thank you. Thank you for a nice presentation. But may I know how much time you took to make the presentation?
Sir, actually, I did not get much time. I was not well since the last week.
Okay. But at least you might keep some images to make better understand.
Yes, sir, I will keep it that way.
Yes. So what are the challenges you find that making this kind of nanofluid? What do you think? I mean, what kind of challenges are facing the researchers?
The main challenges was, sir, that after some time of working, the nanoparticle suspended at the bottom. And is the main problem of stability. There were a lot of study. They find that the stability cannot be maintained for the long working time. So more research is to be done in that direction.
So what's your suggestion to them?
So I found that the use of surfactant helps in stability, and proper vibration, ultrasonic vibration can be provided when working is done on hybrid nanofluid, and we can achieve the stability at some extent.
Okay. Good, because it need more reinforcement, right?
Yes, yes.
Thank you.
Thank you, sir. Should I stop sharing?
Anybody, any other questions? Sarah, sir? Okay, I think Prashant, thank you very much.
Thank you, sir.
We'll move ahead for the second presentation. Second presentation is paper ID 22. Ravichandra Koti. Ravichandra, are you there? Paper ID 22. Yeah, Ravichandra. I can see you, but you're not responding. Okay, so what we'll do, we'll move to the next paper. This paper ID 32. Mr. Ajay Malviya. Ajay, are you there?
Hello.
Yes, Ajay Malviya.
Yes, sir. Good morning, sir.
You can start your presentation.
Okay. Screen share. Just 1 minute, sir. I'm sharing my screen.
Ajay, are you logged in with some other ID? Your name is shown as Arpit.
Sir, it's my cousin laptop.
Okay, so you could have used your ID, na? You can log in.
Yes, sir.
Chalo, you start your presentation.
Sir, is my PPT is visible?
Yeah, it's coming up. Yeah, it's visible. Start.
Okay. Good morning, sir. My name is Ajay Malviya. I am a research scholar in Ideation Innovation Solution in Nagpur. My topic is scope of additive manufacturing in wind energy system. These are the index. Additive manufacturing introduction. Additive manufacturing or 3D printing is a fast-growing industry in which its application has been extended beyond a rapid prototyping by recent technology advancement in wind energy. Additive manufacturing innovation could make it possible to manufacturing a component maintained on a site as well as to produce a site optimized component customized to specify the wind and resources of a given area. For a wind industry, current innovation have the potential to make a substitutional effect on a complex wind component manufacturing, their customization and tested. Resource management is a crucial task in a wind energy system is also have been answered by additive manufacturing in wind energy sector. Because of additive manufacturing, it is easy for us to make a component on a side, and which can help to save our transportation cost, which can also be a benefit for a small and large scale industry. With the help of additive manufacturing, reducing in a time for a design to the product life cycle, directly print a raw material into near net shape part for a wind component, enhancing the part property through microstructure control, manufacturing high complex shapes, integrated a multiple part into a single unit. Potential application of current additive manufacturing system in wind power system. Technology development in a additive manufacturing process are economically viable for a small and large scale wind energy tools and component development. Several application areas have been identified. In addition, if the wind application were used as a goal to push the production of the additive manufacturing system, it might be possible to achieve a further application with a substitutional economic benefits. Application: wind turbine blade shaft facility mold, modification in nacelle cover, advancement in micro channel magnets. Wind turbine blades mold. The first identification application is in manufacturing mold for a wind turbine blade. Tooling is a primary target for the current state of additive manufacturing technology because of its rapid prototyping capability. Mold of a various size and shapes of a wind blade have been produced for a wind industry and tested successfully. Large tooling facility, however, remain out of reach until the development of large-scale component, AM process, and R&D involves in this sector. SWIFT. SWIFT. There is a university which tested and customized the blade according to the geographical area of according to the geographical area. With the help of this, they collect a different data at a different location, and through which they can customize their blade size and get a better efficiency and optimize results. Modification in nacelle cover. Nacelle cover is an important part of a wind turbine blade. It protects a generator and other component from the atmospheric condition, and it's cover and it's cover and it's cover it and it's protect it, due to which there is a lot of heat accumulated on inside it, which is the major problem to reject the heat in atmosphere. So with the help of additive manufacturing, we can design airflow passage and coolant passage through which the heat can be rejected in atmosphere. Advancement in microchannel. With a traditional technology, it is not possible to drill a small hole of a large size. With the help of additive manufacturing, it is easy for us for manufacturing a small size diameter hole and of a larger length. Magnet. Magnet is one of the important part of the wind energy system. With the help of AM technology, we can 3D print a magnet on a side and customize the magnet according to the size of turbine, to the size of wind turbines, to the size of wind turbines blade and generator. Economics. In order to strengthen the supply chain of a wind energy, several additive manufacturing possibilities have been propose. An example, it is an versatile versatile of a customized wind turbine and wind resources component design at a particularly location. Additive manufacturing also provides and customize of different design of individual wind farm for generator, nacelle, blade, tower. Additive manufacturing could allow for advanced aerodynamic modeling, grid interference, and atmospheric data to be used by original equipment manufacturers and component designers. Conclusion: in in the future, additive manufacturing innovation could make it possible to manufacturing a turbine component on a site as well as to produce a site customized component to specify the wind and the grid resources of the given area. With the emerging technologies such as micro 3D printing, high capacity with high additive manufacturing machine is expected to be matched a paradigm shift to a variety of wind turbine component directly could be someday be feasible. Discussion. The main advantages of the use of additive manufacturing for a wind line is in a far more than the blade mold. The use of additive manufacturing allow the design complexity to increase dramatically while saving the material and assembly cost. The future of additive manufacturing tool are expected to have the potential to be used for several process steps. This will bring down the product cost unit. This versatile allow the design to wind component and structure to alter fulfill, including the use of different materials such as modification could be result in the ability to configure the wind turbine at a specific location for a wind resources, also resulting in the on-site manufacturing of different design within the same wind farm. The customization could be lead to be more efficient operation of the entire facility. These are the references.
Thank you, Ajay. Any questions?
Welcome, sir.
Yeah, thank you, Ajay, for your time in presenting. I have two questions. Okay, so first is suggestion. Okay, do not read. Okay, second is make short presentation. Hello, are you able to listen?
What, sir?
No, first question, suggestion is do not read. Okay, make the text less. Make the text less in the presentation. Okay.
Sir.
Yeah.
Okay,
and
sir.
do you think it is feasible to make the turbine blades, whatever it may be, through 3D printing?
Yes, sir.
And there is a conventional technique, molding technique. How far better it is? Do you know?
Sir, with the help of additive manufacturing, it is easy for us to create to customize the blade size according to the geographical area, due to which we can get a better efficiency, and it will help for us because with the help of traditional technique we can only make a certain size of blade. And with the help of additive manufacturing we can changes the shape and design of blade according to the geographical area and the height. So because of it we can achieve a better efficiency, and we can set up a plant on a site, due to which we can save a cost.
Yeah, but do you know the cost of that one? It's not really easy to make such a 3D printed one by using technique. I mean, not really imagine. It will be more than 100 times than a conventional technique. You know that?
Yes, sir. It is. It's need to be R&D.
Yeah, I mean, for example, in the case of mold technique, if you want to make 1,000 pieces at the same level, you can make it. But in the case of 3D printing, 1,000 3D printers has to be work at a time. So which is feasible more?
So, but if we need a different size of blades, so we can go for composite fabrication.
Yeah, make a mold and then make 100 pieces and then distribute among the areas. You know, so in which area you need take a 10 centimeter or 100 centimeter, so you can make. So am I right or not? It's okay. Yeah.
Yes, sir, you are right.
Yeah. Thank you very much. Yeah.
Okay, sir. Thank you. Welcome.
Yeah.
Thank you, Ajay. Anybody, any questions? Okay. Thank you once again. We'll move to the next presentation. Paper
Welcome, sir.
43. Anurag Namdev. Yeah, Anurag, you can start your presentation.
Sir, I'm audible. Hello. Good morning, sir.
Yes.
Yes, I'm audible, sir. Okay.
Yeah, please go.
Okay. Sir, my presentation topic is a short review on polyether ether ketone peak polymer composites. These are the outlines of my presentation: introduction, literature review, objective, materials and fabrication methods, conclusion, application of peak composites and references. Let's start with introduction. What is composite? Composite is nothing but it's a combination of two material. One material is called reinforcing phase and other is called a fiber sheet, that is called the matrix phase. Basically, matrix is the base of any composite material. A material which is composed of two or more materials at a macroscopic scale and have chemically distinct phases. Wood is a very good example, and it is called a natural composite. It is a combination of cellulose fiber and lignin. The cellulose fiber provides strength and lignin is the glue that bonds and stabilizes the fiber. This is the classification of composite. Composite materials can be classified on the basis of matrix material. It can be three types: polymer matrix composite, metal matrix composite, and ceramic matrix composite. Basically, I will focus on polymer matrix composite. It can be three types: thermoset, thermoplastic, and rubber. Next, what is polymer matrix composite? Polymer matrix composite is nothing but it's a combination of polymer matrix with different reinforcement.
Anurag, your slides are not changing.
Okay.
Also make it full screen.
Okay. Change or not?
No, not yet. Slide is changing, but you have to make it full screen.
Okay, sir. So full screen, RI?
Yeah, F5. You can use F5.
Okay.
Matrix composite. PMC is nothing but is a combination of polymer used as a matrix material and different reinforced material like glass fiber, graphite, carbon, aramids, and these fibers have specific strength, means strength to the weight ratio, and specific stiffness to the weight ratio. PMC are very popular due to its low cost and their simple fabrication methods. There are some example of thermoplastic material and thermosetting plastic. This figure shows the common fibers which is used in polymer matrix material. That one is natural fiber and another is man-made fibers. Natural fibers which is comes from nature, for example, animal fibers, vegetable fibers, and man-made is called artificial and synthetic fibers. This table shows the different mechanical properties of different fiber. For example, aramid, which shows density 1.4, elongation 3.3 to 3.7, tensile strength, and young modulus. Aramid, carbon, Kevlar 49, cotton, jute, flax, and lot of fibers. And this table shows the different density, elongation, tensile, and young modulus of different fibers. Now, let's start with literature survey. Basically, I will focus peak composite, polyether-ether ketone composites. GL Petrus et al. Studies about the tribological and mechanical properties of graphene nanoplatelets peak composite. And they concluded that with increasing the GNP concentration, tensile, flexible modulus, and hardness are also increased. GNP fillers provide a positive influence on the coefficient of friction and more especially in the wear rate. The improvement in KK is basically thermal conductivity is around 83% for the GNP 10% peak composite and is associated to its high value of hardness. Next, Dimitrius et al. Studied about the hybrid polyether-ether ketone composites reinforced with the combination of carbon fibers and graphene nanoplatelets. And they concluded that the effect of presence of GNP and carbon fiber on the viscoelastic properties and creep mitigation of peak matrix.
Your slides are still not changing.
Okay, so can we share again? Hello.
You change your slides in this mode only, right?
Sir, will change or not?
No, it's changing now.
Okay. So, Macro Regisha et al. Carbon fiber reinforced peak under dry and bobbin serum conditions, and they concluded that carbon fiber reinforced material exhibited the higher wear resistance compared to the unfilled formulation. Despite the observed difference, were flattened in lubricating conditions. Under dry conditions, annealing treatments affect negatively effect on the wear resistance. Next, Chena et al. Studied about the rate-dependent tensile failure behavior of salt fiber reinforced polyether-ether ketone composites, and they concluded that the tensile strength of peak matrix and peak composites so lately sensitivity to strain rates. Next, Arya Tivatia et al. Studies about the characterization of melt blended graphene polyether-ether ketone nanocomposites, and they concluded that TZA and other properties are increased with an increase in nanomaterials, increased percentage of nanomaterials. Jaho et al. Studied about the effect of surface oxidation treatment of carbon fibers on the biotribological properties of carbon fiber peak materials, and they concluded that the wear resistance of oxidized carbon fiber peak was enhanced due to the improvement in adhesion between fibers and matrix. Next, there are some other authors studied about the effect and size of the concentration of solid lubricant on the tribological properties of polymer peak composites, reciprocating sliding wear behavior of peak-based hybrid composites, effect of varying load condition on the tribological performance of the thermal characteristics of peak hybrid composites, wear and friction behavior of polyether-ether ketone filled with graphene, WS2, and CNT nanoparticles. Next, there are some other papers, nano indentation and nano stretching responses of peak-based hybrid composites. And next is tribological and mechanical properties of amorphous and semi-crystalline peak SiO2 nanocomposites. So basically, this is the literature survey, and after this, this table shows the different filler content and processing technique of peak matrix composites. In first, we can say graphene nanoplatelet is used in different percent, 1, 3, 5, 10%, and the processing technique for making composites is injection molding. So this table shows the different processing technique like injection molding, extrusion process, laser sintering process, compression molding, and the second table shows the filler content, different filler content. And this table also shows the filler material, filler content, and different processing technique for fabrication of peak composites. Objective. What is the objective of this research? The purpose of this study is to conduct a focused review on the synthesis and characterization of polyether ketone polymer composite. Basically, I can say that the basic thing of any research is the basic thing of any composite material is the fabrication of composite. PEEK is a very high melting point containing polymer. In this review, basically focused on the mechanical and tribological behavior of composite. Several research papers have been studied for writing this article. It is clearly observed that the reinforcement of different macroparticle improves the mechanical and tribological characteristics. Also, bonding of matrix material and filler material play an important role on the properties of composite material. The polymer based lightweight component can replace many metal components nowadays in the different industries like aerospace industries, automotive, aviation, defense, medical, wind turbine application, etc. And natural PEEK, its toxicity is low and has low smoke, fire, and toxic gas emissions should it involved in a fire. And now it comes to the metals and method. Polyether ether ketone is ether ketone family group thermoplastic of friction, excellent chemical resistance, and very low moisture absorption. PEEK is a high performance temperature stable polymer that sees widespread use as a replacement of metal in many applications like automotive, aerospace, medical, and energy application. This is the property. This table shows the properties of PEEK: tensile strength, Young modulus, elongation, density, melting point, which I said earlier, it is high melting point thermoplastic material, 343 degrees centigrade, glass transition temperature, thermal conductivity, compressive strength, and specific gravity. Now, there's a lot of technique of fabrication of polymer, but these are some popular techniques which I used in fabrication of polymer composites, that is injection molding, compression molding, extrusion process, blow molding, diaphragm forming, and thermoplastic tape laying. Compression molding. Compression molding is well known and one of the oldest techniques to develop a variety of composition material. It is a high pressure closed molding process. Process is suitable for a small to medium sized part. So, what is the process behind the compression molding? It contains two metal molds to fabricate the composite material. Base plate is stationary and upper plate is movable. Reinforcement and matrix are placed in the metallic mold, and the whole assembly is kept between the compression molder, which is shown in this figure. This one shows the upper mold and two shows the lower mold. Then heat and pressure is applied as per the requirement of the definite period of time. The metal is placed between the molding plates, flows due to the application of pressure and heat, and acquires the shape of the mold cavity with high dimensional accuracy, which depends upon mold design. Curing may carried out either at room temperature or at elevated different temperatures. After curing, the mold is opened and the composite is removed for furthering. That is shown in this figure. Mold, upper mold and lower mold, and then we applied pressure and heat. By the application of pressure and heat, we will make composite material, composite sheet, composite material, different type of composite sheets. What is the advantage of compression molding? Production rate is very high, good surface finish, high form uniformity is achieved, raw material wastage is minimum, maintenance cost is very low, residual stresses are negligible, and twisting shrinkage in the product is reduced. Therefore, dimensional accuracy is very good. Due to expensive machine and parts and the process is suitable for high production volume, it is not economical for a small number of parts. Sometimes uneven parts lines are there and it's a labor intensive process. So conclusion of my work, that is the present review basically focused on the polyether ketone PEEK composite with different filler materials in terms of mechanical and tribological properties, so that we can improve the mechanical and tribological properties for different applications. It is clearly observed that different filler materials are used with different percentages of for making PEEK polymer composite by different method of fabrication, and we can say processing technique also play an important role on the impact of properties and also in the cost. It is observed that many numbers of time mechanical and tribological properties are improved, but sometimes it's so negative effect with filler concentration. When we increase the filler concentration, sometimes it gives negative impact on the properties. Nanoparticles also play an important role for improving mechanical and tribological behavior in hybrid PEEK composite, and there is a lot of possibility of PEEK polymer composite in the field of energy sector also. And this This is the application of PEEK composite in the field of automotive industries like pumps, bearings, thrust washers, balance soft gear, high performance lead-free bushing, needle roller bearings, support rings, and in the aerospace industries like seat essential support, handles, brackets, tubing, pipes, critical assembly. Next, in the field of renewable energy also, the wind turbines, the industry continues to seek a high power, increased torque density, improved reliability, and great work safety. Brakes, roller bearings, cages, and sliding bearings made with PEEK polymer can deliver improved strength to the weight ratio, excellent wear performance, design freedom, and weight saving. In the field of hydrogen energy, in the field of electronic industry like mobile phones, LED connectors, batteries. In the field of biomedical field, spinal cases, heart valves, structure anchors, and in the field of chemical and oil explosion industry. These are the references of my presentation. Thank you, sir.
Yeah, thank you, Anurag, for the nice presentation.
Thank you, sir.
Yeah.
Thank you.
So what is the advantage or other polymers this PEEK?
So first I want is that PEEK is high temperature, high melting point temperature thermoplastic, and it can it can use at high temperature, where high temperature is required. For example, in aerospace industries, automotive industries, where high application is important, we should use PEEK polymer composite.
There are other also, bakelite is there, you know, there are other also there.
So bakelite is a thermosetting plastic and PEEK is a thermoplastic. Yeah. So we can reuse it. Yeah. The thermosetting, we can
Can you use in the electrical, you know, parts for this kind of
yes, sir. In this slide, I will. This is.
For example, you are making some board, you know, electrical board.
Yes,
so can you make it with that?
It's a mobile phone, circuit boards, printers, batteries, computer switches.
No. First question is: PEEK is electrically conductive or not?
Sir, electrical conductive. Sir, I think it is not electrical conductive because, sir, polymer is basically not electrical conductive material. We can use nanofillers and make it electrical conductive material, like CNT, GNP nanofillers.
Are you sure?
Yes, sir. Because sometimes polymer used for the insulation purpose.
So you don't know the polymers which are conductive.
Sir, basically,
list of polymers you know that electrically conductive. Can you give me a list?
Okay, sir.
No, tell me the list. What you know about this electrically conductive polymers?
Sir, there are a lot of electrical conductive polymers, but which I saw sometimes it is used as coating material or insulation material. We use wire as it means metal as electrical conductor in electrical supply or different things.
No, I'm asking a question like, what are the polymers you know that we are electrically conductive, or there is no electrically conductive polymer? You mean?
No, sir. Electrical conductive polymers.
Is existed or not?
Yes, sir.
Existed?
Sir, basically.
Anyway,
sir,
I want to skip this question and you check it, okay, later when your presentation over. Yeah, good luck. Thank you.
Okay, thank you, sir.
Yeah, you will realize later. Don't worry.
Sir, for example, like, sir,
polyaniline, what kind of polymer it is? Electrically conductive?
Sir, like PPV, sir. PPV is an example of electrical conductive polymer. PPV.
No.
Polyphenylene.
Yeah, no, not at all. So they got Nobel Prize for the plastics, you know, conductive plastics. It's okay. Yeah, go ahead.
Polyacetylene. polyacetylene and sir, polypropylene, polyfluorine, like that?
Yeah, there are different kind of
Yes, sir. Yes,
polymers
sir.
which
Yes,
is
sir.
electrically conductive are
Yes,
there.
sir.
They
Yes,
got Nobel Prize for that. Okay.
Okay, sir.
Yeah. So that kind of polymers you can't use for an electrical work,
Yes, sir. Yes, sir.
right? Yes.
Okay. Thank you, Anurag. Any further questions?
Okay, thank you, sir.
Okay.
Thank you very much. We'll move to the next presentation. Paper ID 12. Sony, are you there?
Yes, sir. Hello, sir.
Yeah, please start your presentation.
One second, sir. One second.